The next one I have here is 8.5. 8.5 here is a turbine-related question. So what the question says is, steam is expanded in an isentropic turbine. At the inlet, the steam is of 2 MPa and 360 degrees C. The flow leaves the turbine at 100 kPa. What is the work produced by the turbine? So up here we have a P1 of 2 MPa, and we have a T1 of 360 degrees C. And this is how things are flowing through the turbine. And I have a P2 of 100 kPa. So if I look here for my properties of the turbine at the inlet here, if you compare this to the water table, right, because we're talking steam, we're going to see that the values here are superheated. So if I consider the inlet, unfortunately, the numbers I want aren't exactly on the table. So what I'm going to do is I'm going to interpolate between 400 degrees C and 350 degrees C. And for 400 degrees C, I have an H1 of I have an initial enthalpy of 3247.6 kilojoules per kilogram. And for at 350 degrees, I'm going to have an H of 3137 kilogram. And then I'm also at these values going to look at the entropies. So at 400 degrees, I have 7.1270 kilojoules per kilogram Kelvin. And then I'm also going to have an S of 6.9563. So I interpolated between these numbers. I think the solution just rounded to one of them, if I'm not mistaken. I chose to solve it and with the interpolation. So if I start with the enthalpies, I'm going to set up my relationship so that I have 400 minus 360, which is my desired number. 400 minus 350. And now I'm going to do the ratio of the enthalpies. So it was 3,247.6 minus H1, my unknown, corresponding to 360 degrees. And then 3247.6 minus 3137. If I isolate for H1, I'm going to find a value of 3,159.12 kilojoules per kilogram. That was the enthalpies, and now I'm going to solve for the entropies. What you're going to see is that the entropies, I'm going to set up the same relationship here, 400 minus 360. 400 minus 350. And now I'm just going to do my same relationship, but for the entropies. So I'm going to get 7.1271 minus S1, 7.1271 minus 6.9563. This will give you a value of S1 equal to 6.9905 kilojoules per kilogram Kelvin. All right, so now I have all of these relationships, and I know the turbine is isentropic, right? So at P2, I know the pressure, and I know that S1 is equal to S2. All right, so what that's going to mean, oh, I'm going to need a little bit more space than that, is that I have pressure, and now I have a property, right? And if I look at state 2, I'm going to see that my S2 is equal to S1, and it is between SF and SG, meaning that we're talking about a mixture again. So what I'm going to do now is I'm going to solve for my quantity X. The question, of course, is asking for work, right? And the only way for me oops, I scrolled too far, to equate the work here and through the first law is by using the isentropic relation. If not, I do not have enough information at state 2 to solve for the enthalpy in the system. So what I'm going to say, and I'm going to say that S2 is equal to S1, which is equal to SF plus X, SFG. And these values, again, are from water table at 100 kPa. And so I calculated S1, or NS2, 6.9905. Equal to SF, which was 1.3026. X is my unknown here, and SFG, 6.0568. As my knowns here are S1 equal to S2, they're the same, right? SF and SFG from the tables, which will allow us to solve for X. If I go through my solution, I will see that X is equal to 0.939. Is this a value of X that we would expect? And the answer is yes, okay? Turbines prefer to work with gases because the gas causes less wear on the blades, and the water particles, the water droplets inside the vapor, here's predominantly vapor, right, with the quality close to 1, damage the turbine blades. Okie dokie, now that I have my quality, there we go. I can use this to find my H2. H2 is going to be equal to HF plus X, HFG. In this case, HF, HFG, and X are known. And H2 is my unknown. HF from the table is 417.46. X was 0.939. And I got a value of HFG of 2,258, which gives me an H2 of 2,537.9 kilojoules per kilogram. And for the turbine, if you want to consider the first law equation, there's no change in total internal energy. There's no heat transfer. We are consuming work, right? The turbine does work. And there's no appreciable change in speed, no appreciable change in height. So we're left with H1 minus H2. And this is the expression that we're left with. So because we don't know the mass or the mass flow rate, I'm going to solve for a lowercase w. Oh, this is not. Oh, this is a W dot here, and this is an uppercase W. Now I'm going to solve for a lowercase w, because I don't have the mass flow rate. But I know that my specific work will be equal to H1 minus H2. Which will give me 3,159.12 minus 2,537.9 kilojoules per kilogram. Gives me a work of 621.09 kilojoules per kilogram, which is what we would expect, right? And we also expect the value to be greater than to be positive, which is the case, because the turbine is doing work. It is extracting it from the gas. So we would expect a value greater than 1, which is the case.